Hello, my name is Scott Acton, and this is a talk that I gave at the 2023 Engineering Research Retreat at the University of Virginia. I hope you'll enjoy it. It's called State of the Artificial. I begin with a quote from the late Cormac McCarthy and contend that my main qualification to give this talk is actually curiosity. Back in the 90s, you might be surprised to hear that my dissertation, at least the main article of my dissertation, was published in IEEE Transactions on Neural Networks. So I've been doing neural networks for image and video processing for quite a long time. And since that time, we've arrived at an inflection point. This is an unprecedented time. 2015, if we go back 8 years, a major article in the New York Times on artificial intelligence featured one-shot learning, the ability for the computer essentially to learn a set of symbols, to see it once, and then thereafter be able to interpret those symbols as if they were 1, 2, 3, 4, 5, 6, 7, or A, B, C, D. While this was amazing to computer scientists, it didn't really rivet the nation. Fast forward to 2023, this summer in the New York Times, we're talking about how real people use AI in work and school and more. So real people are actually using AI, and that's due to tools like Chat and Bard and DALL-E, which you've heard about and perhaps used yourself. This is an extraordinary time. Normal people are now using AI in their daily lives. So in my time at the Computer and Information Science and Engineering Directorate of the National Science Foundation, the change was extraordinary. When I got there, my little foundations group essentially saw about a fifth of the proposals by title being on machine learning. By the time I left, just 3 years later, after the pandemic, 2022, machine learning made up 4/5 by title the proposals that we were entertaining. So that's crazy. Look at the journals. The top journals in 2015 aren't much different than the top journals that I learned about in elementary school, or the top journals that people spoke about in the 50s, like Nature, New England, Journal of Medicine, Science. That's 2015. All these look pretty predictable. If we go to 2023, Google Scholar Metrics, which I like a little bit better than the Thomson Reuters approach, we're looking at the same thing, right? Oh, there's some weird ones popping in. IEEE, CVPR, are you kidding me? ICLR, what? NeurIPS? What are these? And there's many lurking below that 10th ranking and rising. So this is a crazy time in which the journals and conferences of artificial intelligence are matching the impact factor of the classics, Science and Nature. I wasn't very enthused by the discussion on 60 Minutes by Sundar Pichai, in which he referred to AI as a black box. I'd like to encourage you, and even today in this next 20 or 25 minutes, to pop the hood on AI and to know that it's not a black box. So this talk, what am I going to do? What is it all about? I'm going to discuss two families of AI, the diffusion network and the transformer. And the company NVIDIA reported that last year, 2022, 80% of the papers uploaded on arXiv on AI were about the transformer. Can you believe it? So that's a pretty exciting structure. Then I'm going to discuss some possibilities for future research, and I'm going to end with my own anecdotes and preaching bits. Okay. Let's start with the autoencoder. I want to demystify the autoencoder at a very top level, we're not going to teach autoencoders here. There's other YouTubes and videos that you can access for such a resource. But essentially, all we're doing with an autoencoder is we're having an encoding side, we have a decoding side. The encoding side compresses a signal into a lower dimensional representation. And if you think that sounds esoteric, you all know encoders, you know PCA, you know k-means. Those are actually encoders. So an encoder encodes into a latent space. We call it a series of hidden variables or latent variables. And hopefully that's a very basic representation from which we can decode, which is we can reconstruct. And one thing you'll notice about the autoencoder structure is that it requires no training data. Essentially, we can compress and then reconstruct and then use some loss function to determine how well the reconstruction went. And so it's something that can be self-supervised in a sense. Now, let's add another layer to the autoencoder and say that we're going to enforce a certain distribution on the latent space Z at the center of the diagram. And what we're going to typically do is we're going to enforce something like a multivariate Gaussian distribution on that latent space. And then, the encoder is going to go from the signal to the compressed version. Then we go from the compressed version to the signal. And essentially, we can do some cool things with this structure. We can do some generative things with this structure because of, indeed, the structure in the latent space. And one of those things we can do is form a diffusion model. And a diffusion model is just simply a cascade of variational autoencoders. So we can do encode, 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 maybe 1,000 times, maybe 100 times. And maybe we go from this synthetic face that you see on the screen to random noise. Then we're in the latent space. And in this case, the latent space has the same dimension as the input space and the output space in the diffusion model. And we can take random noise and then we can take a little bit of noise out, take a little bit more noise out, take a little bit more noise out. And these are all decoder portions of the variational autoencoder. And we can actually get back to a structure which might resemble this fake person's face. What we can also do is we can just do the bottom portion of what we're showing, and we can generate from our own randomly generated noise new faces, perhaps, if we've learned the structure appropriately from maybe a series of 1 million faces. This is the variational autoencoder used in a diffusion model. And what's cool is that the forward process is nothing more than just adding noise. We can do that. We've been doing that with MATLAB, with Python since the beginning of time, right? So we've been able to do that for a long time. And the reverse can be something as simple as a UNet, as the decoder portion of a UNet. So nothing complicated, and we can do some cool things. Some of the cool things that are going on in the literature and in the field are upper left. What if you could take a segmentation mask, an abstraction, a cartoon, and actually make a real image? Well, people are doing that with diffusion networks. What if you could take an undersampled, blurry image of a child and get the high resolution version of the child? People are doing that. And what if you could make bizarre new faces? Yeah, well, people are doing that. One thing that my group likes is that you can actually take a random point cloud, and after training the network to form certain shapes, you can form airplanes or furniture or whatever you're into. Turns out we're into the patterns that that proteins make within a bacterium. And I'll show you that at the bottom. But at the top, what my group is doing is we're taking not additive noise and removing it, but what we might call multiplicative noise, signal dependent noise that you might encounter in radar or ultrasound. So we're using the diffusion process to essentially enhance SAR images, in this case, synthetic aperture radar images, to a level which was not possible even a few years ago. It's pretty amazing. And here's one that's in progress that we don't have perfect results for yet. We're taking the reports of position from single molecules that fluoresce within a bacterium, and try with a diffusion model, we're trying to compute the actual trajectory, the actual path that this that one protein takes through the cell. And in fact, we're interested in the speed at which that protein moves. There's a couple things we're doing. So that's diffusion models, basically based on variational autoencoders. I'm trying to demystify and fear you from these concepts. Another one is the transformer, and I'm going to talk a little bit about the transformer in the context of ChatGPT 3, if you will, which is basically a fancy autocomplete machine. And we can actually take the application programmer interface for ChatGPT 3 and do something like make an input. The best thing about AI is its ability to, and it's going to give us perhaps 5 possible results. And these possible results are ranked. And ChatGPT won't always take the top one. It won't always take learn. It might, based on a temperature. Higher temperature is crazy. Lower temperature is more predictable, more conservative. It might take, it might say the next word is do, which has a significantly lower percentage than learn assigned to it. And so all of this I learned from an article on by Stephen Wolfram, who I've been following really since the late 80s. Pretty amazing guy, and you can get his paper online. What is ChatGPT doing? So this model can be repeatedly applied, and you can apply it once, you get learn, and then you apply it the next time, you get from, you apply it the next time. It decides experience is its ability to learn from experience. The next time it adds a period, and then it continues on and gives you options on how to complete this entry phrase. So let's look into what's going on here in ChatGPT. Well, first of all, let's understand the input and the output. There's only about 50,000 words that we use in the English language in a typical case. And in fact, there's about 50,000 tokens that are assigned integers in ChatGPT. And right now I'm talking about ChatGPT 3, for example. So the input to the system, which we're going to call a transformer, are tokens, which represent various words like the. It might also be parts of words like ized, or pre, but think of the tokens as words. And then also the positions. If I say the quick brown fox, the first token is the second one is brown, or I forgot quick, and then brown, and then fox. So there's an ordering to those words. We're going to encode that internally into the vectors that go into the ChatGPT transformer. And that's a cool thing about it. The tokens are immediately converted into features that we're going to call embedding vectors. And these embedding vectors are quite rich in the sense that for ChatGPT 3, we're talking about 12,288 numbers that are 10 bits in precision. So the positions, which I'll talk about, are added, and this might be counterintuitive, are added to the embedding vectors, and I'll show you that. Then the transformer network can consume these token embedding vectors simultaneously, because the position and the embedding are all enclosed in the vector that is used as an input to ChatGPT. So I will explain that in brief at a top level in just a second. So what's an embedding? It's hard to visualize a 12,000 number or a 12,000 dimensional embedding. It's hard to envision 5 dimensions if you want to go there. So I'm going to take a 2-dimensional snapshot, thanks to Wolfram, and show you an actual portion of the embedding, ChatGPT 3. And you can see that words that relate to each other are near each other. And so this tells us about the relationship of words. Alligator and crocodile are very close to one another. And I can't even tell the difference between an alligator and a crocodile. I never lived in Florida or Louisiana. But you also see apricot and peach, or you might say apricot if you're from the Midwest, perhaps. So words that relate to each other are close in this embedding. So word comes in, it's just an integer. Let's say 712 represents the word the. That integer gets converted into embedding that has a vector of length 12,288. Then what we do for positional encoding, let's say I'm encoding the phrase, I am a robot, and that's what I'm giving to ChatGPT. Who knows what it would say? It would say something really clever after that, I am certain. But I would be in the 0th position, robot would be in the 3rd position. And what we're going to do is, and let's just say for grins that instead of 12,000 numbers in each embedding vector, we have 4. And that's going to be the 4 vertical columns you see on the right here. And so these are the positions within the embedding vector, and these are the positions within the sentence. And so we're going to take sinusoids and we're going to say the position within the embedding vector is I, and it's going to affect the frequency of the sinusoid, and the argument of the sinusoid is actually going to be K, which is the order of the word in the sentence. We're going to take these numbers and we're going to add them to the embedding vectors. And the best way to visualize that is to visualize that. Let's say we had embedding vectors of length 512, and we had, say, about 100 positions. We had a paragraph that had 100 words in it or 100 tokens. This color-coded are the positional encodings that we're going to add to the embedding vectors for each position and for each element of the embedding vector. And so it's a simple addition, make embedding vector, then add positional encoding. And a cool thing about this positional encoding is that we can definitely tell relative to one word to another that this word occurred 5 words before it, or this word occurred 5 words after it. You get it. But essentially this relative position is now encoded. Let's say we're going to do a translation. My French is lacking, and let's just say the French phrase je suis étudiant was the input phrase. An étudiant or student is telling us what I am, what je. So étudiant gives attention to je. This is the concept of attention. What words are related to each other, and how can we put these words in context? This is the power of the transformer, attention. And attention has 3 elements. One is query, one is key, one is value. Let me explain them very quickly. A query could be étudiant, student. What word is étudiant giving attention to in this phrase? And we call this self-attention because it's within the same phrase or within the same paragraph. So then we're going to look to the keys. The keys are the states of the other tokens, including étudiant. So we're saying, who's out there that gets attention from my query? Well, je does, because étudiant tells us what je is, what I am. It tells us that I am a student. And essentially, the only thing we're doing is basically a correlation. We're forming a product between the query and the key. And so it's a simple matrix product. You see it over on the napkin on the right. And so I'm just doing a simple, if there's 3 words, je suis étudiant, it's going to be a 3x3 self-attention matrix that you see over here, simply a product. And maybe we don't like that product just being random numbers or big numbers. And so we're going to scale it. And then we're going to also make it in the form of a distribution that is summing to 1 and having no value greater than 1 or less than 0. And that's what softmax does. Pretty simple. We've been doing that, since high school, forming distributions. So query and key product, after some normalization, if you will, are going to make attention. And this attention filter is what we call it, is going to be applied to the values. It's going to weight the values, which are the actual embedding vectors of the tokens after some weighting. So basically, the attention module is going to produce weighted values weighted by attention, which is simply the product of query and key. The transformer is going to use these weighted values as the input, and this allows, in natural language, context to be captured. So, for example, I might say, server, can I have the check, please, because I'm polite. In this case, server is a transactional word. I also might say, looks like I just crashed the server. Well, in that case, server is a computational word. So self-attention, the relationship between words, and maybe the words are crashed in server and check in server, are essentially giving us context, and we can understand human language with a machine. So just at a little more level of detail, as I showed you, we're going to take query and key, after some linear weighting, and we're going to do a matrix multiplication pretty much straight up. And you're going to get this attention matrix. And the attention matrix might be telling us about self-attention for the phrase, when you play the Game of Thrones. And I think, I'm not a fan, but I think you live or die. And this is going to occur across multiple heads in parallel, which I'm not going to show you. But after we compute attention, which is a product, we can all take a product. I don't care who's watching right now. I know you can multiply. 3 times 3 is 9. I still remember that. And then we're going to normalize. And how are we going to normalize? Well, we're going to put it through a scaling factor, a multiplicative factor, and then also run a softmax on it, which makes basically every row and every column in this matrix sum to 1. So, well, at least every row in this case will sum to 1 after the softmax operation. And these softmax values will be applied to the actual values, the actual features that are, you see that in green, the linear weighting of the actual features. And then after we compute attention, after we normalize, we put it all together, and that's our attention weighted values that are also going to be weighted once again and consumed by the transformer. Okay, I'm going to make the transformer very simple. We talked about encoders and decoders earlier in the talk, and here I'm going to also have an encoder decoder model. Even though, I might have 20, 30 layers of these encoders and 20, 30 layers of these decoders, and I might have multiple heads of attention, just let me simplify it for a second. We're going to take je suis étudiant. That's our input. There's going to be a token, an integer number for each one of these words. Then there's going to be an embedding for each one of these words. Then we're going to compute those sinusoidal positional encodings that any MATLAB program could compute for you. And so when they're embedded with the position, that's going to be the input to a self-attention layer. We just talked about a self-attention layer, which involves, a matrix multiplication, weighting the values, and some modification with some weights after that. And this will go into a traditional feed-forward network. And then eventually we're going to get to the latent space where we have latent space vectors. And in this case, let's say 1 for each word. These latent space vectors are going to be the input to the decoder side. And the decoder side is going to go through a similar self-attention mechanism. And the only twist is that we're going to have another stage which allows attention that's not self-attention, attention that goes between the input and the output, which we call encoder-decoder attention. And I'm showing you that on the right. It's basically the same mechanism of computation of correlation, but let me move my face a little bit. And you can see that, for example, I and je have very high attention. Am and suis have very high attention. The English word a has very low attention with everything else because it does not have a friend in the French phrase. And of course, étudiant has high attention with student. So, this is just showing you the relationship between words in this translation example. It's very similar in an example in which we're doing autocomplete, probably just a little less glorious on the encoder decoder attention side. Okay, so attention, so the mechanisms of attention, the positional encoding, the embedding, and the structure of the transformer give us basically the backbone of what happens in ChatGPT. There's a lot of other bells and whistles and heuristics that go on that I can't cover here. All right. In my laboratory, we love video processing, and right now we're collaborating with Peter Young's and the Education and Human Development program at the University of Virginia on an educational application. Here's the application. We want to find out what human activities are going on in the classroom. And we're making the argument that simply taking the natural language paradigm and applying that to video processing is a mistake. Why is it a mistake? Because things move in images, is one idea. Things move. Things are semantically meaningful. Some things are semantically meaningful. Some things aren't. In our videos, humans are very meaningful, as are the objects they manipulate. So humans are the queries of our system, and humans and objects are the keys in our attention system. And we allow a multimodal process, which also encapsulates optical flow, our motion, to affect our classification. What's our classification? There's a group activity going on in the classroom. The teacher is holding a computer. The teacher is doing one-on-one instruction. And this is a grant from the National Science Foundation, and we're pretty excited about this research. It's basically a video transformer for human activity recognition. Let me tell you about some opportunities for future work that have been brought up by my colleagues, Vipin Chaudhry, our own Adong. He was my colleague at NSF and a great guy. And then at UVA, Adong Zong and Hongning Wang were contributors. And there were 40 or so other people that contributed to this document that was from an NSF workshop in 2023. So essentially, they proposed a number of barriers in existing AI, a number of advances that could solve those barriers, and some recommendations to the community. I'm going to concentrate just for a few minutes on the barriers. So in terms of barriers, there is a lack of large-scale labeled data. As you know, machine learning is very hungry, and it's also prone to overfitting in the scientific realm. What do I mean by scientific realm? Medical, biological, chemistry, as opposed to the Amazon and the Netflix commercial realm. So we're going to get lower signal, higher noise in the scientific world, fewer samples. So a good idea is to go with simulated data to train. And that's what we're doing with the Gallman group at UVA Chemistry. We're simulating images of biofilms that contain hundreds and thousands of bacteria so that we can learn about their behavior in a group, for example. So this area, I think, has a lot of promise, the development of simulated data for training. Causality is a big problem in the machine learning world, in my opinion. What I just told you about was correlative, was attentive. And so attention gives you relationships between, say, two words, but it doesn't tell you if a protein caused a disease or a disease caused a protein. It doesn't give you a causal relationship. And these relationships can be quite complex. And we might ask what came first, the chicken or the egg. Machine learning in its current state isn't going to help you here. A couple of my colleagues, Miao Miao Zhang Jundong Lee are doing some work in this area, and I hope my group does as well because it's a cool area. Explainability is something in which we have a long way to go. We want to understand why things mess up. We want to understand how things work. And so we don't want the black box of Sundar Pichai. So how we understand and interpret is really going to be the key to trustworthiness and adoption. And really, there's no mathematical basis or accepted basis for this right now. I'm working with Natasha Shabani of UVA BME, Shine Musa at the UVA School of Medicine to explain why planning results for or guidance results for focus ultrasound go well or don't go well. And this is an amazing technology, and for the most part, it's going really well. But we want to be able to make sure that we can explain the results when we use AI. So I want to encourage cross-disciplinary result, and I want to encourage you that when you pursue cross-disciplinary research, that you don't let the scientist, if you're the computer scientist, treat you like a data processor, and you don't want to treat that scientist or that application person as a data source. Person A has to make person B's work better and vice versa. I've had that relationship with several of my collaborators, including Andreas Gallman, where we challenge each other and we actually make the sum of the parts greater than the simple sum, and that's what we should pursue. I want to get mathematical for a second. I'm going to introduce a lemma. My lemma, based on my work at National Science Foundation, is you can't ignore AI. You don't have to do AI in your work. You don't have to do it, but you can't simply ignore it. You're going to have to treat it in your proposals. You're going to have to say why it's not relevant or why you compared to it and your method was better. So another lemma is from my friend Fred Epstein, and he says a proposal will be more successful now with current AI than if you're using some old version of AI that maybe you took from grad school or maybe you borrowed off the shelf. And the corollary to that is that you're not going to get funded in 2024 by applying UNET to medical imaging. It's already been done, right? So what I'm saying is I'm encouraging a collaboration, and I work at UVA Engineering. I don't know where you work, but we're going to be more successful if we have competent AI users teaming with competent creators to get the state of the art. And I admit that these groups are perhaps overlapping. Some people can do a little of both. But what I'm encouraging you to do is to collaborate. If you're a user or at the application side, to collaborate with somebody who really knows their stuff, machine learning, and for a machine learning person, not go the distance on their own, but to collaborate with someone in the application end who has an interesting problem. Maybe that's a problem in democracy, or maybe that's a problem in medicine. I don't know, but that's what I'd like to leave you with today. Thank you for bearing with me, and I will stop at this point. Thanks very much.